Hi, this project is related to nonlinear multi-machine transient stability assessment using the classical swing dynamics and with the fault dependent network topologies in MATLAB. Basically, in this article, we have just represented the complete nonlinear electrical power expression for the electromechanical interactions among the interconnected synchronous generators through the time-varying susceptance matrices, which representing the pre-fault with fault on and post-fault network conditions. In the pre-fault with the fault on and post-fault network conditions basically identifies to save the cost with the time during the maintenance during the operational operation of the machines. Okay, so in our section we have used the three machine system which is simulated to evaluate rotor angle, divergence, speed deviations, and the center of inertia for the behavior of um, severe disturbances. So in MATLAB we have just defined the complete power system stability, uh, which is basically the scientist name is Kunder, provided its classification stability equations, and the study integrates the basically numerical ODE solvers for the equilibrium linearization to examine the eigenvalues based stability. In our results, basically, we have generated that how fault duration network with the configuration of critically influence, synchronizing the torque and damping as well. Okay, so I have written the complete abstract with the keywords and the introduction. In the introduction, I have just added the monitor the rotor speed with its angle, with its generator terminal voltage, its power, electrical power, and during the power system stability analysis, we have used the Ford algorithm. Ford is basically one of the scientists who presented the transient energy function method for the power system stability analysis, and in the model generator dynamics through nonlinear relationships between mechanical input power with the electrical output power and the coupling of strength governed by the network substance matrix. So during the fault condition also we consider the electrical topology undergoes abrupt change, creating fault on and post-fault operating conditions that significantly modify the synchronizing torque and the damping as well. So here is basically the complete uh, introduction in which I have detailed explained that how the linearize the representation around the pre-fault equilibrium as well as the instability mechanism, which offers two foundation of developing the advanced control techniques for future resilient power grids. Okay, so here is the background of power system stability and the classical swing equations as well, which is basically these are the equations I have used for the power output results for the motors rotor angles, for the angular velocity as well. This is the angular velocity, and the multi-machine system modeling. These are the machine parameters used in our case in terms of susceptance, time-dependent topologies, network topologies, and this is the fault dependent networks. Basically, the fault dependent networks provide us the complete three-phase short circuits network topology, and during the fault conditions occurred during the disconnection, during the grounding, during the changing the effect of elements in network, So here is the table basically, and then pre-fault rotor states with the peak rotor states during disturbances as well. Here is a nonlinear dynamics and stability assessment according to the swing curves of machines for various current ratings. Okay. So the problem statement accordingly, how we need to synchronize the leading to loss of synchronization, how we check the traditional linearized approaches fail to capture these nonlinear effects, and these are the mathematical approach, how all the mathematical equations are added here in terms of electrical power, in terms of angle, its speed, its angular velocity, pre-fault, fault on, post-fault models as well. Okay, so these are the linearized model with the methodology as well. It's all the parameters are available in terms of this section. It's classical swing equations used in our section. These are the classical equations used in form of table. All the symbols are added in it. Okay. Yes, we have just used the MATLAB ODE 45 solver, providing the time domain trajectories for all rotor angles and the speed. And in terms of MATLAB algorithm, we have used COI motion and the eigenvalues spectrum for the fault clearing times, which varied through determine the critical clearance time. We called it shortly CCT, and in MATLAB visualization enables a detailed inspection of the oscillatory patterns of the potential instability. Okay, so the design of MATLAB simulation analysis with the this is basically methodology. Okay. Okay, the MATLAB methodology is same. Basically, MATLAB design simulation methodology is same. Like I have just explained how we represent the polynomial homotopy continuation method to locate all power flow solutions basically. And here is the output results for the rotor angle deviation relative to COI basically. COI basically is the center of inertia. Okay, so the COI angles is a good reference for the analyzing of system stability. Here is the rotor speed deviations as well, and the graph, which is basically electrical power with the mechanical input PM basically. Here is the individual machine angles as well, and the individual machine rotor speed deviations with the center of inertia angle and its speed. Okay, here is the eigenvalues of linearized pre-fault system output results, and with the results of discussion like how electrical and mechanical power varies in different machines, and how the linearized system eigenvalues through pre-fault, through fault on and post-fault conditions occurred, and these are the conclusion with the references. Let me just show you the output in terms of MATLAB simulation. These are the MATLAB code. You just need to run this section and you will get the output results like eigenvalues of linearized pre-fault system. So basically this code takes some time, so that's why I have just run before. And to check the output results, these are the first figure, which is rotor angle deviations relative to COI, center of inertia, rotor speed deviations with the electrical power PE and the mechanical input PM. Basically, I have added the legend as well. PE1 means this blue line, dotted blue line. This is a dotted blue line, and same with the PM2, PM3, basically mechanical input, which is basically solid line of sky blue. This is a line of sky blue. Same case of individual machine rotor angles relative to COI, center of inertia, in terms of different angles, and the individual machine rotor speed deviations with the center of inertia angle and its speed. Okay, speed is represented the dotted line of orange lines, and the blue solid line provide us the center of inertia angles in degree. This is the eigenvalues of linearized pre-fault system in terms of complex plane. Okay, so if you need to ask anything, you just ask me. I will answer your questions. Thank you.